Remember where we were? We did some big picture stuff 2 lectures ago on how to do hypothesis testing. Then we went into convolution, which I think you have to hear once, completely internalize and then never forget, and always do. And then we did a whole lecture on the mechanics of using convolution to convolve functions, not generate any data, not work with any numbers other than with the shape of the functions which we claim to be PDFs. And we cheated, and I want you to cheat in this homework within the honor code, which is to generate a normalized function that is never negative and that you can just shoehorn into whichever x interval you want. So I made it so that whatever the outcome of my multiple convolutions, I went right back to -4 to 4, only for convenience, okay? Let this not be wrong. If you remember when we did the whole illustration of why the distribution of the sum of two variables is their convolution, we went through this example of involving two uniforms. Well, there's such a delay between my finger doing it and the camera showing it, but it goes from these two boxes between 0 and a to a triangle between 0 and 2a, and clearly that keeps on growing. That's not the exercise here in the homework, because we don't want to just keep readjusting your axis. I mean, you could if you want to. So we're just dealing with the shape here. We're not making any more inference than that. So maybe here for my own table of contents, I'll write here that we dealt with the exercise of successive convolutions to just evaluate their shapes. In mostly MATLAB, I suppose. I did it all in MATLAB in my video example. A little bit of a recap, something that I figure if I mention here, it's going to make more sense if I mention it now. Okay, you all know convolution now, and I don't think I've used the word, but it's going to come. I slipped my tongue. People talk about this filter, this impulse response of that filter, this thing that you convolve with. If you think of X as a series of, pushes on your therapeutic mattress or something, and H on the impulse response of how your depression rebounds from that over time. Kernel is another word, okay? And that is just one of the many things that are called kernel, and you always ask what people mean. If somebody says, don't you know? They don't know that kernel is used in so many different contexts. So you play that right back to them, okay? But, and that's because I was gonna ask, all right, what would be the convolution kernel if I wanted to say, do a moving average where I average every 2 data points? I'm asking specifically because I know you're all doing it, and somehow sometimes it escapes people how naturally this is related to convolution. A 2-point moving average, what's the kernel? I'm going to rewrite y of n as a convolution of some input sequence with a certain kernel, and I want y to be the moving average of the signal x, where the average pertains to 2 points at the same time. To smooth something, like if you look at the weather or your stock exchange and you say, give me the moving average over a day, 5 days, a year, lifetime of funds. In this case, the kernel is given by what? What would you convolve a sequence of numbers with to end up with a new sequence that presents the average of every number on a rolling basis? Anyone? Is anyone seeing this coming or not? And I'm not finished writing my equation down. Okay, so if I write it, then you have to think about, oh, does that make sense? I'm saying I'm just going to write a little vector of numbers. I'll say, well, how about a half, a half? If I roll this around, and by the way, you may not be Latinist, but convolution means literally rolling stuff around, and that's how I imagine it. You are rolling this kernel around your data, wrapping its action around and shifting, spitting the output out. So if you give it X, I'm not going to write it out. You want to write this out on your own. I'll write it in a slightly different form in a second.
Can we have, let's say, delta of k plus 1 and take off and sum till n minus 1? Does that work?
At this point, I'm just saying that this is what it is, and I want you to imagine why it is true. So I don't need now any delta function because I have already assumed that my X is a discretely indexed digital variable. Not that you're implying that, but just to further clarify. So this is a discrete sequence. It's again, you pushing your mattress and recording the rebound of it. So it's like you take two things at a time and you replace them by the vector product of 1/2, and it take half of the one plus half of the other one. And then the second value is half of the second one plus half of the third one. And the third value is half of the third one plus half of the fourth one, and so on. I'm extending my thought a little bit before I'm going to narrow it back down. As soon as I think about moving average, I want to add that I'm going to think about moving difference and call that G. Now my question is going to be simple. What's the convolution kernel for a moving difference?
1/2 and -1/2.
Yes. Just like the moving average produces a sequence where every number is the average of two numbers. And if I start counting at 1, it's the first one is the average of 1 and 2, the second one of 2 and 3, of 3 and 4, and 4 and 5, and 5 and 6, and so on. Now, switching the sign, I will turn it around and say, well, give me the moving difference of 1 minus the second one, and then the second one minus the third one, and the third one minus the fourth one.
Why would this not be 1 -1 then?
Oh, why do I have the half in there?
Yeah.
Oh, because you are totally right in my looseness of terminology. It turns out that if the average, I do want to divide by 2, right? In the moving difference, really, I'm implying by symmetry that I'm going to do an average difference. So there's my 2. So it really is 1, 1 and 1 minus 1. It's same, same, or same, negative, same. Okay, you're absolutely right. And so it's difference with a grain of salt up to normalization, but all these things are up to normalization. Here I normalize by 2 because then it makes it an average. If I had 3 elements, I'd say a third, a third, a third. The larger point I'm trying to make is that you have to imagine that these can be arbitrarily long. You can make up yourself any form of an averaging function, including, you know, -1/2, 4/3, you know, 2/1, and that's some sort of by extension an averaging function. And if it involves lots of minus signs, then by extension we all rope that together under moving difference. So these are examples of such functions, and they are always up to normalization, which means the bottom factor up to normalization.
But how could we normalize something that has a sum of 0? So
you could normalize the norm, and you're taking the words right out of my mouth. You very often would present the action of these operators and say, well, what is the length of this vector? And this is actually not a normalized length. It would have to be squared root of 2. But I could normalize this by a length, and then I would divide it by another factor. So it's like you're setting a trap for me in an exam where, like, I use one word, now you're using the words against me. It's like, yes, right, this is an average of 2. This isn't a difference. This is a difference, you know, divided by 2, like the average was. And then I'm saying, yes, up to normalization. And really, I mean up to by this divisor, because you can define by yourself what the quantity is And let me just repeat that this, like moving average, I mean a convolution if it's two with a like apple apple versus apple negative apple, and you decide what the size of that apple should be or how you express it in whichever unit. But you're reading up about filter theory later, people will most often just say you want to normalize the length of it, which means the square root of the sum of the squared elements. But I didn't want to take it this far now. And also moving is with a G, unless you work for Duncan. But now think about this as an incoming data stream. You know, it basically came from nowhere, it goes on forever. And so here you have X, and I'll just say X2 and X3 and X4 and X5. And what I'm now attempting to write is the matrix form of this general type of operation, also knowing that it's going to, you know, be an infinitely long thing if you want. But the important part is that, look, if I say I'm here at this point in my sequence, and I'll say I want to have the sum of X4, I'll do it with 1, and X3, and then the next output I want to be the sum of X5 and X4, I'll do 1, 1, and the previous one was, you know, X3 and so on. So if I, and now just do the normalization at the end. So if I had the notion of a infinitely long, constant diagonal, zero domain matrix here that I want to call big H, and now I want to call my data vector big X, or how about just X singly underlined for it being a vector, and I want to call my output vector Y of X, then I hope that I have introduced a fruitful notation whereby the column sum of this matrix is just a sum of the little elements in little filters. So 2 at a time. But the convolution, it repeats that operation. And so you want to flip the filter backwards and then roll it around down the diagonals of this matrix and then keep going forever. And the output only ever gets you the combination of 2 elements, but they're 2 successive elements of moving averages. And so now if I say give me the moving average of 3, you just add a 1 here, and then I want to normalize by 3 or square root of 3 or whatever you like, that's no longer relevant. What's relevant is that convolution is a linear operation. If it is a linear operation, and I do it on a discrete set as this is, then I should just be able to write it as a matrix equation with a simple dot matrix product in between. And I could read off the constancy of these diagonals from that equation, but that's not always that clear until you write it down. So here I'm trying to write it down, that the structure of this matrix is constant diagonal banded. And for good measure, I'm now going to write a similar thing for a moving difference. And I'll do just generic elements. And you know it's going to be constant. And I will write them like this. And I'm going to gloss over some of it. I just want to have the symmetry here. And I'll just call this big G times X. And let that outcome of that be a Z. Okay. And so a discrete time convolution, it leads to a banded constant diagonal and otherwise zero matrix operation where the outcome of convolution is just the matrix vector product of what you put in with the response of that system. And the response of that system has, for every row in the matrix, the filter in it, that kernel in it, shifted and copied. So I really am supposed to try to give you a word for this also, where you will find this in the literature. People recognize this and name this toplets, okay? Toplets matrices, entire books are written about them. And it's gonna come back when we're doing Fourier theory. So what did I wanna say with it? I want to make a fruitful connection between a matrix notation, a matrix vector product, and a convolution in the same way that you're actually doing it, but if you write it down, it's just sort of a little bit more painstaking. I want to make sure that you all know that these things are distinguishing themselves by the values of these filters, and that if you arrange them in a matrix that you're characterizing that system just the same. I do not want to quibble over the factors of 2 or square root of 2 or whatever it is, because it is up to you to decide what you filter with. However, much filter theory is orthogonal or orthonormal, and so then you end up with definitions of what that normalization factor should be. And yes, that is, but then really by extension using the term difference, when it really already is an average, and really maybe I don't even want that. And for, you know, fun, I just want to mention that apparently this is one of those exams that they give you to get a job at Google or Facebook or something. It's, you know, the question is as follows: can you reconstruct a signal if instead of the x's, you're getting the moving averages and differences? Is there any information lost if you have both those outputs, and can you get x back? And if it's a coding job, they'll ask you, and can you write a little algorithm that does that by replacement of elements without requiring any more memory? And so the answer is yes, and it's going to take us too far, or rather I'll return to it at some point. But so it turns out that if you have a signal and you keep the moving averages and differences, that you can indeed completely reconstruct it. And this is the first building block of a whole series of conjugate mirror filters, as they're called, which leads to all sorts of interesting theory that I wasn't going to bring up, but now it's only sort of in my head. Quadrature mirror filters, the Haar transform, these are things that you'll encounter at some point, and then it will make sense that you've heard them here first. The completeness of perfect reconstruction, those are all the words that are in my head now. The ability to completely and perfectly reconstruct a signal from its averages and difference, which isn't, you have to prove it, not immediately obvious. And then the last, well, I like this game, you know, I bring to mind what comes to mind, and all these things are in the class and will be in your future. I think I have used the word filter just today. So these are finite filters. And so filter theory is independently interesting, and we are going to need it later. Finite or infinite impulse response filters, invertible or non-invertible filters. This, of course, plays into whether you can reconstruct a signal from its filtered version. Let me play a word game and ask, if I say filter, what do you say? What words come to your mind? As in, like, give me another word.
Smoothing.
Smoothing, I like it. I'm gonna write it. This averaging, that's a smoother, okay? Definitely. What would be the corollary word for the difference? I'm just gonna say it because you will read it, I think, in Menke. You know, and of course this is a sort of made up word, but this is a roughening filter, right? That's this here, okay? Give me other words that if people have used the word filter with you, they probably would have said at least 1 or 2 more words around it to help you think about what sort of filter they're actually talking about.
Like a low pass or a high pass?
Yeah, okay. And so a low pass, a high pass, and a band pass are types of filters that let low frequencies through passing, or high frequencies through by passing, or passing within a narrow or wide but finite band. And so now I'm going to ask you, is the smoothing and roughening, where do you put those words low pass and high pass on? On which ones?
I would say that those would probably go towards smoothing in
Well,
my
pick
mind.
one each. Tell
One
me
each,
which.
okay.
I'm gonna write pass on both, and you're gonna tell me if it's low or high.
I would imagine that the rolling average is low pass and the moving difference is high pass.
So yes, and hopefully that makes sense to people, but this is my job to connect in your heads, right? Low pass means, what is low? Well, the frequencies are low. We haven't even talked about the frequencies, but you've got to start imagining that if you smooth a signal, that turns to long wavelength, low frequency information that smooths out spikes and whatnot. That's why you ask for a smooth time series when you look at the weather or your financial time series or something like that. High pass does the opposite. It accentuates difference. In time series, same thing. You're like blowing up an edge to like, whoa, it's really jumping at you. In Photoshop or any other image processing software, this is edge enhancing, whereas low path or smoothing is blurring. Actually, those are other words that I'm going to need here. So blurring, those are all words that they all mean all of that. And blurring versus edge enhancing. Okay, so we're in this sort of domain where statistics and matrix theory and image analysis and time series analysis and Fourier analysis and linear time invariant systems, you know, it's all the same thing. And I'm going to finish this train of thought here by saying, well, if I told you that I replaced my weather time series by a rolling average where I did some sort of an average, could be a triangle function, right? Could be any sort of function. As long as you end up with a low pass behavior, that's the extension of what it means to be moving averaging. Or vice versa, a moving differencing. If I wanted to somehow undo that, if I wanted to unconvolve, then, well, that has a name too, and that is called deconvolution. Deconvolution. And this is the segue I've been looking for to build into what I really wanted to talk about. First of all, to teach you the word, and the word is not to deconvolute. The word is to deconvolve. So now I want you to think about how on earth you would write this in this box type of equation, right? You kind of, I don't even know what to try, telling you how to write it properly. But maybe here, this is more promising. If I tell you, look, convolution is just a linear operator with a matrix. All that matters is to write down what the elements are, and they're going to be the rows composed of the filters that you apply, and then it's going to just shift around, roll around the rows, okay? So with that said, I'd like to put a word here that says deconvolution is in essence what?
Like reconstruction?
Yes, but does imply that it's somehow broken, whereas, you know, if I'm saying edge enhancing, maybe my new version is actually better, but it's true. But I want you to use a mathematical word that helps me see how I can recover X from Y. So yes, recovery, or yes, reconstruction, and so I'm going to write it here, recover, reconstruct the X from its corrupted or possibly enhanced Y or Z, the thing that I have done to it. And what I done to it, I've linearly multiplied it with a matrix called big H or big G. Does that trigger any more words that you might want to use in this context?
Inverse?
Yes, I want inverse. Because if I told you in scalar form that some y is some number h times some number x, and I say, could you please give me x? You'd say, yeah, I got it. That's 1 over h times y. That's a scalar form of doing anything like this. It's just in matrix form now that we have a linear relation, and the word applies. We want to invert the relation. And I want to use the word because this is the subject of the whole next chapter is we want to invert relationships. And the best way I can see to illustrate it is to do exactly this, you know, deconvolution, you know, there's my example. It was a linear operation. It was of a very specific kind. I can write it as a matrix product. In principle, I should be able to, you feel that you want to try to write it as an inversion. And you also hopefully, and you're going to get there in a second, see immediately that inversion may be hard, it may be impossible, it even may be undesirable. for reasons we can get into. But something like inversion is going to be needed to do this reconstruction of an x from its linearly transformed variables, because this is a good example for it. And hopefully when I say inversion, you reach back to some interesting matrix theory you may or may not have had, but even if I say invert the number 3, then you know that it's 1 over 3. And if I say invert the number 0, you know that you are going to have a mental breakdown. So whoever wants to say, oh, just divide by the number needs to immediately say, well, what if the number is small, right? Or relatively small, or very, very small, or exactly 0, then immediately you need to have that reaction that it's going to need some work to do that. And we are going to definitely be discussing it. And this is the first example of one that's immediately needed. Okay, so I think that is possibly more interesting than details of confidence intervals. And so let me ask you now at this point, we're going slowly, which is fine. I want you all to read the 2.7 thing on confidence intervals, and maybe I will talk about it, and maybe I could do that now, or I could actually just sort of go a little bit further and say, well, it's time that we do some model building, and that's sort of where I would be ready for. So do I take a step back in a half an hour, or do I take a half an hour step forward? What do you prefer? Send me your chat. And if I do the hypothesis testing, it's the last bit of statistics, because all the rest will be statistics applied to whatever else we do next. And then I still may bring it up later. You all want forward. Forward it is. Done. Okay. So what that means is that we are doing inverse problems. Generally, very generally, you have to think about the fact that the reality that you want to know, the earth that you want to study, the process that you want to illuminate exists in some sort of abstract model space. You know, it exists, all right? It's true knowledge about the earth, let's say. And there is some kind of a mapping to the thing that you actually do, which of course lives in data space. And that mapping, I'm just going to call forward mapping. And in a nutshell, model building, parameter estimation is to reverse this arrow and to figure out what the inverse mapping is, whether it even exists, whether it's possible / even desirable. But that is also known as science, right? There's data, you want to know something about it. You do not want to know anything about the data because you already have them. You want to know what the data tells you about the world that you want to study. Let me just talk about M, some generic model space, and let me talk about D as a symbol for a generic data point or set of points or continuous thing or whatever it is, something data related, something model related. And let me call that forward map G. And this is a very fancy G. And the model maps onto data in this way. Okay, examples. Well, one of them, clearly we've been talking about all along, is a linear model, okay? Convolution is a linear model. Moving averaging is a linear model. Why is it linear? Well, when I talk about G of some alpha times n plus some beta times n, just like in your expectation little problem, that's going to have to map through to G multiplied alpha G of n plus beta G of n. That's linearity. For A and B constants, for alpha and beta constants. Let me give you an example that is pre-convolution. How about this example? D is of an argument, I'll make it of x, is going to be some integral of some operator. I hesitate even to talk about function in some arguments that take the model, which also now receives some kind of a coordinate, and somehow puts it together like this. Okay, I've just written a completely generic integral with something called g that, don't mistake the little b here, that's an integration measure, but so it takes a model, it applies something to it. This is an integral model. You can think of a continuous model parameter like temperature of time, and it produces data. And yeah, just like before, this G is going to be called my kernel. And believe it or not, when people specify this in the geophysics literature, they'll talk about the Earth filter. All right. This is an integral equation. Again, there are entire books written about this that don't even mention the word inverse theory or geophysics or anything, but it is basically a generic form of something that says, look, this is a relation and you know elements of it, but you want to know the other elements of it. Presumably you've all done some differential equations that say, oh, the derivative of m is the sine of t, find m. That is a different differential equation that you solve through, generally integration. This is an integral equation that you solve through, well, not really differentiation. You know that's much harder to solve, but that's the broad topic here. So, special example. What are the coordinates of this mythical function, which could be how heat propagates through the earth or how a pollutant works its way through the soil? This could be a function in two variables, but only dependent on the separation of the two variables. No more comma, no more two independent coordinates, but rather something that expresses that whatever happens to it only matters, only changes as the separation between what you're applying it to matters. So what sort of a kernel do I get when I write a generic kernel in x comma y variables through an integral equation? And now I'm saying, actually, the specific form of this particular g is, it's a function of x minus y. What sort of thing comes to mind if I want to specialize this special example of a special relationship to a g function that is a function of separation?
Sounds like the moving difference.
Could be. The difference is not because of this negative here. That ultimately has nothing to do with it. The difference would be in the g. But I'm going to liberally interpret your words as saying that's the form that we call convolution, right? And the moving difference was an example of convolution. I had the integral equation at some point, didn't I? Yeah, like this. Here, well, look. Now, x is my kernel. X would be g. And now I have a dummy variable, k, another k. How about I say it like that? And the difference matters, right? So as soon as I've said a g shall be existing in two variables, and then, but actually the two variables are only, occurring in this function into their separation, then I've defined again what convolution is. And then you can say, well, the g could be some differences or whatnot, and it could be this or that. And I've already also used the fact that what I initially started as defining as convolution, the convolution of h and x is identical to the convolution of x and h. So you can switch those arguments and you can turn that into everything you want. That's the only point I want to make. So other special example, let me just give you a discrete and linear example. And then I'm where I want to start. So when I write these curly g's and so on, this is about being continuous functions, but perhaps functions of variables that can take any value like pi. When it's discrete and linear, I'm going to start developing my standard notation here that, again, I'm going to have some matrix operation. And it's going to work on some discretized model space, which I now write as a little vector. And I'm going to say it produces data that I have, okay? And I might actually already also give you my next set of favorite symbols is to say, well, look, the data is really going to be, I have to assume now, I now tell you that M is the truthful existing population, the model space, that thing that I want to obtain. G is how I see it. In this particular case, I've discretized my model space, the temperature in various rooms. And G is how I sample it with my thermometer. And D is the data that produced. But I actually may go and I'll say, we're going to also maybe have this representation where I say, well, really, the data, I'm already preparing you for going backwards in statistics and saying, well, look, the data are going to be signal plus noise. And we're going to try and unwrap the influence of noise on this relationship. But for now, let's just stick with this relationship, which is the forward model. And the objective is to find M, given G, which is called the experiment. That's how your data see the truth. And given B, the data that you collect, find M. And don't just find M, also tell me how to find it, and tell me that you have found it and that it is good enough, and that the quality of how your data constrains this model, etc., is in appraise the result. So that is the inverse problem. Real example? Oh, I hope images like this, it really does bring me back to being, 8 years old or something, where at some point you do learn about mappings and what a function is, and whether something is one-to-one, whether you can invert this by writing the arrow backwards. Does that trigger in your mind things like some pieces of the model space may map onto the same thing in the data space, and that's going to be really hard to undo, but if it's bijective, it's going to be really simple and easy, and if it's surjective and injective, those are all terms, I barely do remember them, but that is sort of in the set function theory that draws upon. And that's going to become clear very soon that not all of these mappings are immediately doable. How about I give you a real example that you can do something with, and that'll be as follows: a worked example. So this is simple. It's really just something like this. I have time, let's say. I'm collecting data as a function of time. I have Newton's law applying, which predicts that, I don't know, if I throw a ball into the air, it's going to have a parabolic trajectory, which I'm drawing to the best of my ability. And your data are where that ball is. Of course, that's not on the line, because maybe your eyes are bad. Maybe it's going really fast, blurry. You know your model, the assumption, your working hypothesis, your idea of the truth is that the data of this independent variable t are given by some linear model, and I'm just going to call that, a couple of coefficients, a plus b times time plus c times time squared. Okay. Yes, this is a quadratic function. This is still a linear model. Sounds strange when I say it, and I'll show it in a second. So, all right, well, that's my functional relationship, really. And my data is basically y of t is what Newton says, okay? Newton says, throw a ball, it'll be quadratic. If you say quadratic, that's a polynomial with 3 terms, you need 3 coefficients. One of them is the gravitational acceleration. So you then say, well, I'm going to go measure that. And you're saying, well, my model here, is that my data? Is this y here, is the truth, plus some noise term. And right now, I'm not saying anything else about it other than, for now, just ignore it. This is going to be very important. It's the reason why these data don't fit the model perfectly. Right? If there was no noise, we'd be mostly out of work. But let's just say this is noise, contamination, unwanted stuff. Not just what you think of jitter, but also perhaps the things that the model doesn't describe. Anything not captured by the model that says, this is the relation. Okay. So let me try to come to the point here. If I stick my data, because it is easiest to write it as a vector, I stick my data point 2, 3, and 4 into a matrix. I'm now building the G matrix, doubly underlined, and I will write this as a linear relationship, claiming that I could. I'm just going to do it. And previous notation was this is M, the vector, and this is D, the data vector. And there's the dot product. Okay, what goes in the model vector M? So I want to fill M with symbols, and you can pick any symbol from the page.
Can it be Y?
No, because Y is really conceptually much closer to what D should be, right? Because D, the data, is what the model says it should be, plus whatever contamination I have. And now I'm writing straight down that D should be some relation between some other things, and M needs to be my vector of model parameters that I want to know.
The constants A, B, and C?
Okay, I'm going to want to put them here. I'm going to try to put them here. Okay, so if that's the case, what do I put in the columns of this matrix? What do I put to match D2 in the first column? What do I put right here in the first column, the row equivalent to D2, that illustrates the relationship between the model parameters and the data?
Would it be on the diagonal, like 1t and t squared?
Only if you let me cut the word diagonal from your sentence. It's a row, right? So 1t, 2t, 2 squared, 1, t3, t3 squared. So on the rows, it's exactly like you were saying. It's the number 1, because D2 has to be 1 times A plus B times T, the second time that you have, plus C times T squared. The third data point is 1 times A, and so on. So that's matrix multiplication. And I think I have written it before, but remember that we talked about I think we did talk about it, how to multiply a vector with a matrix, well as G, I, J, N, J, sum over J. So whenever you see a dot product, and you want to write it in index notation, you supply enough indices. And whenever you see a dot, you join them together, which means that really was the same index. And if it is the same index, it's a product, and that means you need to sum over those products. That's all wrapped in that notation. It's very easy in the end. And so the ith data point is the sum of the jth column element on the ith row of G with the jth element in the unknown parameter vector M. And I have M, big M model parameters. And so all of what's on the board here is consistent with what I wanted to do. With that caveat that I might want to go back on my, what did I say? I said data is a real relationship plus noise. And so the real relationship is what I want. I want the model parameters. And so when I said GM equals D, I kind of really should say, I should have said, and then we imply that we noisily observe that relationship. I'm going to fix that here. But let's just go back to this here. Newton says that if you take times and you observe trajectories, that the physics model of the Earth is quadratic, which means 3 constants. Now you're making an observation of it, which I call data, that you as a scientist say corresponds to the model, but perhaps noisily observed, or maybe you're missing terms, and then we'll deal with that later, and so I've been ignoring it. I want to write that in a matrix notation. What better way than to just write one of those relationships and then another one, and then split the term such that it becomes a matrix multiplication, which, if we didn't already know, is coming from an index notation like this, or however you like to remember it. I mostly remember geometrically. I barely remember. I find this to be cluttered. I remember how to write it, but I don't like to write it. I much rather think about, going down the columns, going down the rows, and that sort of thing. But you will have different ways of learning that stuff. Okay, well, so that's the essence of what this inverse problem wants to do. We have entered in the realm of the Menke book, for sure. I think you open it on any random page and work backward to where you start recognizing it. We also have walked into the territory of the Astor, Borchers, and Thurber book. And we're also about to walk into the territory of the Gubbins book. Now, I will be here as your trusty guide, but you will want to take a look at these things too, if you want to have an idea of where this is going. Okay, let me just make a couple of comments. What is to come is, well, you're going to tell me how to make this model, right? So I'm going to tell you how to invert G, but you're already seeing that G is a rectangular matrix in this example. It has more rows than it has columns. None of you should know how to invert such a thing by the thing called inversion, because that doesn't work, right? We will need to discuss about what it means to be a good fit. We will need to look at the role of noise, and we will need to look at when such a thing doesn't work. And so I'll just start writing it. When the number of model parameters is smaller than the number of observations, you have a well-constrained, in principle, so-called overdetermined system. It really doesn't mean that you can do it, but it means that you can try. More observations than unknowns. That's what we're definitely going to deal with first. And that most typically is associated with the word regression, although I personally don't like to use that word regression because it's too vague and it could mean a lot of different things. But you will find books exactly about this that are called regression analysis, and that's clearly what it relates to. So I'm going to write that word here anyway. But we shall progress and not regress. So next week, I'm going to tell you more about how to solve problems like this. I'm going to give you some more examples, and I'll just keep talking until you stop showing up, I guess. So read that stuff. I think now we have moved forward. Let's not go backwards, and read the remaining chapter on these hypothesis interval. It introduces one more distribution, which it's too hard to prove, so you got to take it on faith, but that is the student distribution. It also more or less organically shows you why, again, the chi-square distribution arises. We're asking for confidence intervals on the mean and on the variance from a sample. And then the big thing that I want you to definitely take away, which I would have spent time on showing you again, is that if you look at what comes out at the very end and says, oh, I've taken 47 observations and my arithmetic average is this, that must mean that the mean of my data set, the expectation of my data set, is really plus or minus this interval, that is an additive interval of uncertainty. And you go through the same analysis for the confidence interval on the standard deviation, and all you do is work out what it is, the same ways. And there isn't an addition that comes out, there is a multiplication that comes out. And it has to come out like a multiplication for something I said early on, right? The sense of scale is multiplicative. The sense of location is shifty, additive. I'm going to just show you. You open this thing, 2, 1, 12. You're supposed to find this a little bit scary because, you know, there's too many symbols here, right? But the true variance, which you don't know but want to know, probabilistically lies within a bigger number and a smaller number. And you use something related to the data, something you construct, the so-called statistic, the so-called sample variance, as ways to construct it. And then if you literally just work out, it is not hard, it just, you know, got to keep track of things. Then the confidence interval scales like this, where there is a chi-squared that depends on the number of observations and so on. But the important point I was just making is that there isn't a, it's this plus or minus that. It's between two scaled things. Very different from the confidence interval of a location, which end up as like plus or minus, where mu, which you want to know, lies between two values, which comes out like something, well, it just did come out, that was it. The plus and minus is a very different relation than the times and divided has come out of, well, this is not going well, this scrolling. Anyway, there it is back, right? And so that needs to forever be, nobody should ask you what is the plus and minus on your variance. It's always a multiplicative uncertainty. And then later on, it's going to be logarithmic and so on. Senses of scales are multiplicative.